Well, welcome to everyone, both familiar faces and new people, particularly, who we haven't seen before. It's very nice to have you here and join us for this conference. Throughout this conference, you're going to see a lot of technology and ideas and details as well as zoomed out views of what's happening. But for this talk, I really wanted to zoom out still further, and I wanted to think about some fairly basic concepts of computation and how we're looking at how to address those, and see how we can drive further into technical process. So that's why I've entitled the talk Injecting Computation Everywhere. And the idea is, how can we drive, in a sense, technical progress with ubiquitous computation? If we manage to have computation doing all the things that it can do, how can we drive technical progress as far as possible? So that's really the subject of what I want to talk about for the next few minutes. And I guess I want to start with a question. We all take the idea of being able to compute things as something that just has always been there. But actually, in terms of mechanized computation, it's pretty recent. You know, last 50 or 60 years is when that's really kicked in. The idea that you could really compute something with a machine. Of course, the idea you can compute something by hand goes back a lot further than that. But even that isn't a natural idea to people. You know, if you ask the average child whether they can work something out like that, they wouldn't necessarily think so unless they've been educated. So one question is, it's a powerful idea. It's so powerful we take it for granted. How much further can it take us? What can we do with computation, maybe that we haven't immediately thought of doing? Where can that go? Where can that theory of being able to take rules and move them further, how far can that take us? Well, I thought it would be useful to review a little bit about what's worked well in the world so far for computation. And I think, you know, I put down, you probably have some other categories one could put down, but let me go through these. Traditionally computed computational domains. So things like physics. You know, how did the planets go around the sun? That's worked well for a long time as something that computation could handle. Things that we do on pencil and paper worked well with computers. You know, writing down basic sums, doing some basic algebra. Mostly these are things that are very well-structured models, where it's very clear what the abstraction of the model is. You can be very clear, you can write things down in a very constructed way, and then you can apply the rules of hundreds of years, potentially, of working out how you take that question, in a sense, and turn it into an answer. And also simple to specify questions around data. Things where you can ask a relatively obvious question about data and you can then get an answer of it. So those have worked well for a number of years with computation. Let's talk about things that are still to develop. I would say sort of top of the list in some sense is things with fuzzy questioning. Things where we'd like to get an answer. We know there's an answer in there. We know there are things we could work out about it, but we're not quite sure kind of how to get to that through the data or through the model. You know, rapid deployment of new ideas. So oftentimes you know there's something to be computed, but it's kind of like, how do you rapidly get to the point where you're really producing the answer there? How do you compute? How do you get everyone up to that speed, as far as they can go? You know, another thing, again, which is troublesome, remains troublesome, is how you communicate with computation. Can you communicate active, interactive things, or do you have to communicate with traditional, you know, papers or documents that are dead? These are things that are still not quite there in many ways. And sort of the utility of modern data structures. So traditionally, most things have been kind of, you know, rectangular. It's a matrix, it's a grid, it's a tensor. But actually, in the modern world, that's not really what you would like to do. You'd like to have data structures that represent the data, models that are set up to be actually to do with the thing you're modeling, not in some very rigid format, because that helps you to move those things much further and understand them better. So those are a few of the things that I think are still to develop. And maybe you have suggestions of other things as well that are kind of on that list. Now, it's also interesting to review just a little bit that sort of computational technical progress have had an iterative history. So what happens is, some piece of science or engineering advances. That may actually cause computation to advance. For example, if you make a computer that works better because you've discovered something new, but then the fact that you can compute more opens up new areas of progress. So the fact that you can compute an awful lot means we can now handle big data. We couldn't do that before because we couldn't do mechanized computation. So what you find is that you're getting this sort of ping-pong between computation and technical progress. Sometimes it's iterative, it's sometimes also recursive, and that's a very powerful sort of ping-pong, and we need to go on pushing that, but it's sort of not obvious always to see where that's next going to go. So I think my message is, we've done a lot with computation so far, but there's a heck of a long way to go. There are many, many new channels of computation that are going to open up over the next years and decades, which will just make what's happening today seem very basic. And the way that what's happening today makes what happened 20 years ago or even 10 years ago look pretty basic. So I wanted to take, we had a sort of special focus at this conference on data science. That's not the only area where computation is applied. But I think often when people are working with computation, in the end, you either end up producing some data or you end up using some data to make models. Either way or both. So I think it's a very important area and one that clearly is developing very fast. So I wanted us to talk through data science expertise and kind of what we should expect and what the issues are there to give us a kind of a case study. So let me ask a zoomed out question again. In the world, has more data led to better decisions? Questionable. Right? We have a huge amount of data around the world now, and you'd think that that would mean all the decisions were much, much better. It's not clear it's panned out that way yet. And, I would say one of the problems right now is there's information overload. I mean, some of us even remember before the web, right? There was kind of information underload then, right? You couldn't get the basic data very much, and that was a problem. And everybody was scrabbling around just trying to get basic information. Now the problem is we are all bombarded with huge amounts of information. We can find virtually whatever we want. But we all feel it's kind of overloaded. Oh, if only we could figure out the stuff from this information that we could really figure out, then somehow we'd be better and we'd be able to make better decisions. And by the way, the problem is getting a whole lot worse, right? Because we're clearly going to be generating much more data than we are now. If you just look at your own analytics, when you're tracking yourself as you run around and everything you do in life is somehow tracked in some way, which you may or may not like, but the reality is somehow that data is potentially being collected. And the question is, can we use it proactively and positively as opposed to negatively, and can we actually use it? And so the mountain of data is going to get much, much bigger. So let me summarize that today's data challenge, I think, in order to get, in the end, what you want out of these things is decisions. Right? In the end, you want to know how to change something you're doing. That's the reason you're doing all of this work. And so in a sense, today's data challenge is, I would say, these sort of three things. Can you make available data accessible? Can it actually be something that's accessible, not just out there? Various governments, particularly the UK and the US, have liked to throw data out and make open data. The problem is nobody can really use it. So that means the data is available in principle, but except for a few specialists, it isn't really accessible. They're very different. Also, taking average and making it personalized. So this is a huge sort of change in the way people, in statistics in particular, think about things. Can you take a sort of average situation? On average, our age is X. But the real question is, given that your age is Y, what is it that the following characteristics, and given that you have all these characteristics, what is true about the best guess of your situation? And, so I think the summary of those is making obscured obvious. You want to take stuff that seems obscured and make it kind of very obvious. So I think one solution to help this is indeed highest level computation for everyone. And what that means is, many of you guys are specialist computation people. You are people who are very into doing technical analysis. you need to have stuff optimized for you, but you also need to be able to produce stuff that's optimized for people who are less technical than you, so that everyone across organizations and your customers or clients or whoever it may be, or your students, any of those people can sort of operate at the highest level of computation that they're capable of doing. And that requires different ways to handle things. So in a sense, one of the things I'm saying in data is that we need to sort of empower the knowledge community, the consumer of knowledge, to generate their own knowledge. See, often what happens at the moment is if you're consuming information, you don't drive yourself. You're just given something, you look at it. The question is, can you kind of drive? Can you be interacting with what you've got? And that's kind of what I think an important direction is for making better decisions happen. And one of the things that's notable is that expertise has kind of got personal over the years. So if you look back into sort of history, there was a time when you got somebody to type everything for you, and then word processing came along and you did it yourself. There's a time when, you made, graphics, you had a big graphics department making things, etc., etc. The web did various things. The web actually was really two things. I think it was personal fact-finding. It was also sort of distributing information personally. Photography. And now I think, for the last year or two, we're talking really about personal knowledge generation. And the question is, how can we empower that? And in a sense, it's also connected with personalizing data science expertise. So let's talk about the barriers to this. What's stopping us make this go further? Well, I think there are roughly three. One is the technology ecosystem. We'll be talking about that more later. I think we can help a lot with that. Another one is, there are various elements to that: interfaces, deployment, computational power, coherence. I'll come on to those. Computational data, setting up data so you can compute from it with a computer. Seems obvious, but it's not what's being done in most places. Most of the data pumped out by most people is sort of for humans. And also something, the subject of my talk later today will be about how people can improve so that they can operate in this new climate of modern data science. And in fact, I was going to talk specifically about data science education. I think what I'll talk about instead is vision for global education reform that Wolfram are embarked on, including this. So how do we think about how to address these problems, particularly the technical ecosystem problem, and move forward? Well, I always think a great start for any of these problems is to think about the interface. What, in the end, is what you're going to produce, and how is the person on the end of it going to use it? What would you like their interaction with it to be? So I think if you start with asking that question, that always is a help to working back and figuring out whether you can build what you want to build to do that. So there are many, many interfaces. And of course, one of the ones that we've been involved in is what you might call linguistics, where you are trying to type something in and get some sort of result. So if, for example, so make this full screen again, sorry. Let's go. So let's do something like cows in Germany versus population of UK, or let's say London, actually. And let's see if we can get an analysis of that. And there we go. Oh, it seems like London has fewer cows in it than Germany, or people, or whatever, actually. And the graph is sort of interesting there. Anyway, it seems like there've been I guess people have increased faster than cows there. Anyway, now, of course, as well as linguistic access, another interface is voice linguistic access. So if I ask my phone the same question, how many cows in Germany versus population of the UK? Except I changed the question.
Let me check on that. Okay, check it out.
Okay, and so if we do that, courtesy of Apple's Siri, you can probably just see on my iPhone screen, it did in fact work it out, except I did the UK, so I guess that's a larger number. And you can see that we produced that answer. So that's a typical kind of linguistic query where it's kind of like you just want to talk to the thing, you just want to get a quick answer. It's a kind of drive-by querying of data. And obviously that's something we've pioneered, but there are many other interfaces too. Another thing we have done quite a lot of is knowledge apps, things where you want a narrative and you want the user to be able to drive. So you want to give them some sort of narrative to drive by, but you want them to have some control. And a typical example of that might be a sort of interactive report. This is one by Seth Chandler, who is an economic lawyer. And this just looks like a normal paper, you know, in the way that, actually, no, sorry, this is not that. So this is a different report. This is a health report. Actually, this is a rather interesting one. This is a report of a Middle Eastern country, and this actually is anonymized data of real results. So you can test yourself against the actual population. So here we are seeing, you know, if I've got these LDL and HDL levels and I'm a smoker, here's my actual risk of different sorts of disease, of heart disease. And this is actually modeled directly against the population. And, you know, it's kind of nice. I've got a paper, I've got a, you know, here it is. It looks like just a dead document. But it's actually doing a highly complex analysis here that's giving me real information out. So that's what I mean by the kind of the knowledge consumer driving the knowledge. So one question you need to ask is, what data are you working from? And one of the problems at the moment is a lot of people are working from, you know, the focus is, can I make a piece of data that a human could read? You know, an Excel spreadsheet, for example. The trouble with that is that data isn't usually set up very well for what I would call citizen computation. It's not set up that well for people to actually use a computer like I have to work directly from. And so you've kind of got to work this from both ends. You've got to get the data set going so that it's usable immediately by the computer, and then you've got to have the right computer interface for people to use it. And it's very cool when you do that. I mean, this is a simple example. You're maybe aware of this. But if you ask, for example, in the human genome, where does this sequence exist? And depending on how long or short I've made it, we'll see whether such a sequence does exist. Oh my gosh, I've picked one which essentially just has 2 positions, I think, on the genome. And anyway, so you know, there we did. We searched the human genome. It was already computable. We asked for that combination of base pairs, and there we got it. That's where the site is. That's the sort of power you have when you have computable data. And I must say, actually, I'm very rarely pulled out. Normally, I do the length so that it's like, when I've done this, so it's either very long or I get nothing. But so there we go. Now, we've been trying to help with the process of actually getting the data in the good shape to start with, as well as what we do when we compute it. So this year, we launched Datadrop. And Datadrop is, in a sense, a way to make an instant computable database. And whether it's from a device or from your own kind of collected data, the idea is you can get things directly from this. And one of the things we an example actually made at a rather nice hackathon in Spain, I believe it was. This is the so-called Boris bikes in London. And these are bikes you can rent, as in many cities, to move yourself around. And this is, so we did a pull from their API every few minutes, and we dropped it into a data drop, and we then plotted around London where the bikes go during the day. And it's kind of interesting, because I guess in the morning, everybody goes like to the city, and so all the bikes are full in the city and empty outside. And in the evening, it all goes the other way. And then I think there's some effect of the fact that bikes tend to go downhill, because people prefer to cycle downhill than uphill. So the point is, though, this was a very quick and easy simulation to do. Just a few lines of code, and you can get to this sort of result. In the middle of that is the sort of data drop functionality. And I think that's kind of a nice example of how easy you can make it when you have data working correctly. Another thing we're trying to set up is a data framework, so you can set up your own data in the right form to be computed immediately. And that's the Wolfram data framework. And I think the more that data can be set up that way to start with, the better things can work. Now, one of the things that's allowed us, one of the things that's funny to me is that, in a sense, people don't think of Wolfram as having been central in data science for 25 plus years. But actually, symbolic expressions, really, and they're just a sort of very flexible data structure. And so actually, we find it very easy to represent any kind of data we want to, and much more cleanly than, as I said earlier, these rectangular systems. So it's kind of interesting to remember that, in a sense, everything to us is data. Data is the same as functions, is the same as models, because they're all symbolic expressions. Now, it's kind of cool what you can do if you mesh everything together. And one of the things we learned, we made a few weeks ago, actually, is this image identify site. And the idea is you can put an image in it, and it will identify the image. And it's learnt stuff with machine learning in order to produce this. And so there, for example, it's figured out cheese, and it can pull stuff from Wolfram Alpha. And it's pretty nice that you can wire all these pieces of technology together. Now, I'm hoping to go one step further here. And let's see. Let's try and do an actual live computation here. It has correctly identified that I'm a person, so that's a good start. Now, the mystery of the pineapple is we will test the pineapple. Oh my God, range hood, that's probably what's behind here. Joinery, well, that's not bad. I have not tested a pineapple. Lampshade. Edible fruit, well, that's not too bad. Pineapple, there we go, we got it. Maybe I should zoom out a little bit. So you get some, actually it did pretty well on pineapple.
Next to it, see what happens.
Yeah, okay, well no, I think it'll get horribly, well let's try it. Whether it picks up person and pineapple or just edible, I'm all edible fruit. So, and you can have some fun with this. I mean, what's cool is that one can really, let me see if I can, scalpel, ball, cutting implement, rugby ball, oh, I see, I guess it did look. And so I guess you can get disc, it's coming, but it's kind of confusing. Disc and circle. Anyway, you can play with this for hours. Frisbee, I think Frisbee's probably the best. Anyway, it's pretty cool that all of these things can be joined up, and it's exciting that we've been able to manage to make such a thing rather easily and produce, the mixture of the language and the data science and the recognition, et cetera, has managed to produce that. So let me summarize about data science. I think, lessons about computation from data science, there's a long way to go. We're only scratching the surface, and we've gone decently far, but we've got a lot further to go. There's huge power from a sort of single unified environment. And in a sense, having everyone be able to access it, like I could hold a pineapple up to my camera, is an important part of being able to drive empowerment, because you need lots of people to be able to interact with the data in this case to be able to make that work. So, what are the steps that we see to injecting computation everywhere for everyone? What are the things we think we need to do in order to achieve that? Well, let's start with what we've got. The thing that we've got that really, really helps this is one unifying system of representing everything. That's only really, really coming to life now, 25 years plus out from when we started. And, as you know, many of you, if I write maths, you can represent it in a functional symbolic way. If I write graphics, you can represent it in a functional symbolic way. They all look the same under the surface. And the fact that these are all represented the same way gives tremendous power to what we can do. And that, in a sense, now more recently, Datasets have joined as a new element of the setup. But these things all interact in unexpected ways. Images interact with data, interact with semantic recognition, interact with all of these other things. And the ability to be able to do that is, massively multiplies the power of each thing. So another key technology that we are really driving forward on very successfully now is the hybridized cloud model. I wanted to talk about what people talk about as cloud. Obviously, in the world, people talk about the cloud. And software companies in particular say we've turned our software into cloud software. And the question is, what does that actually mean? I think what it often means is you can store stuff in the cloud, or sometimes you can run something in the cloud. What we mean by cloud is compute, store, share, deploy, universal access, any or all of those things, some of it local, some of it in the cloud, whichever combination you want. So that's why we've named it hybridized cloud. Because to me, the real power here is not by saying suddenly we could give up everything that's local and put everything in the cloud. The real power is to say, there's combinations of cloud and local that optimize what we want to do, and actually you want that optimization. To give you a simple example, if you want to pull a slider, unless you have a very fast, low latency network to go to some cloud device, it's not going to be as smooth as it is computing locally on your machine. On the other hand, you don't want people to have to install stuff locally on their machine in order to run something with a slider. So one of the problems we've had with computable documents, as you may know, is that it's required a local installation of a plugin or similar for somebody to be able to run stuff. The cloud stops that being a problem because the computation can sit remotely and you can simply have a web browser. Anybody with a standard web browser can run interactive manipulates by having it set up on the cloud. Will it be as smooth? Depends on their latency and bandwidth and so forth, but it will work in a very nice way, and that immediately enables you to deploy interactive documents and applications to people everywhere, knowing that they can definitely get to them. So that, to me, is a good example of where kind of a hybridized model works really well. Now, the other thing to make clear is we are also taking our cloud technology and turning it into private clouds. So the idea is that although you can use our services in order to run cloud computations or all of these other things that I mentioned, you will also be able to get a version of that to install in your organization. So effectively, you have your completely own setup. And again, that's extremely powerful. In fact, that's particularly powerful because some of the issues over latency and so forth, if you're locally inside your own network, actually go away when you have cloud technology locally. And so therefore, you really can kind of have an environment where people just using browsers and things to go a very long way. So I think that opens up a huge, and I know we've had fantastic interest in private clouds from around the place, and particularly in Germany, where people are correctly concerned with their security and things. I think that's a very interesting development. Now, another key technology that we have been talking about recently a lot is Wolfram language. We launched this as a separate sort of item, so to speak, last year. Really, Wolfram language has been brewing for much longer than that because it's been inside Mathematica. But what we've done is turn this into its own standalone type of language. And it's worth remembering just, what it offers. It's literate, so you can immediately see what you've written, much more than most languages. It's sort of multifaceted but unified, and it's also, it was in an era already when it first started emerging, where kind of like the human trumps the computer. It's like very early languages, you're so worried about the power of the computer that you made the language very close to what the computer understood. And the problem with that is it makes it hard for the human. But we're in a modern world where, frankly, for the most part, computer power is kind of more than we need in many cases. And so, not always, but in many cases. And so it's more important to design a language that works well for humans, even if it's a little bit more effort for the computer. And of course, then you want to optimize it anyway so that, in fact, the computer runs fast. And often, after a time, you can optimize it sufficiently that you can actually do really, really well in making it just as fast as it would have been if it was sort of very close to the computer. So the principle has always been that, and of course the key thing is that the language is very much attached to computation. And so the computation's kind of ready to use that. And that seems a crucial thing. And I know over the last year in particular, people have really been latching on to the idea of the Wolfram language and thinking about Wolfram language in comparison to other programming languages, not just to other computation software. And so we've had a lot of people talking about how to use it instead of Python and instead of Java and instead of other things of that sort, where they hadn't really thought of it as a language before. And I think the power of that will grow more, particularly as we have the cloud applications growing more. One of the things you may have seen in the last year is Tweeter program. And this was a program to be able to tweet, and maybe some of you have done this. The idea is that we have such a powerful language that in 140 characters you can actually tweet a meaningful program. And so as you see, there have been 12,500 nearly tweets, and these are all the programs people have come up with that work in 140 characters. So I think that's a kind of a nice demonstration that we have a highly compact language from which you can do a huge amount in a very sort of short run. Now, one of the challenges we've had is that we have an awful lot of emerging technologies. Many of you will be familiar, in particular, have been keen users for a long time of Mathematica, and the core technology there underlies all of these other things. But actually, we have many of these different pieces emerging for different uses, for different sets of people with different functionality. And so we have all these products emerging, and the project we're now embarking on is how do we piece these together into an ultimate computation system? So we've got the ultimate underlying piece, we've got the core unification of the language, and we've got many other pieces that are very unified. But we also want productization that is useful for many different groups of people. And so the key sort of question is, how do you piece these together to get, in a sense, both ubiquity and unification? And one of the things we've been thinking about for a long, long time, I've shown this diagram before, is when you productize things, do you make them discrete products, or do you make them sort of a continuous swathe of products across everything? And we've always believed that you should have this sort of unification. So, you can look at these different things. There were graph and network systems. There are high-speed numeric systems. These are peaks that, in a sense, were above our technological level. But over time, we try and submerge these peaks. And, the idea is that over time, our overall system actually can do better even at the specialized ends of the spectrum. But even if it doesn't quite hit on some particular area, you don't have to build too much on top of our system in order to be able to supplant the very specialized areas. And one of the things to note is if you are in a specialized system, kind of on the top of a peak, and you want to do something just a little bit different than what's on the peak, it's a long way to fall if you're in a traditional system. As in, you've got a long way, and it's also rather uncomfortable sitting on a spike. So it's very important, I think, to have this sort of continuous functionality across all of these areas of computation. Now, one of the problems with piecing these things together is that it's harder for us than anyone else. Why do I say that? Because, on the other hand, the power that we can get out of that is also dramatically more. And it's a unique opportunity. Well, the reason I say that is because of this, what I call dualities and hybridizations. So one of our problems is, which is great problem to have, but it also makes my life hard, is that we don't have discrete sort of differences between, let's say, development and deployment. If you look out there, most systems there are either development systems or they're deployment systems. They're not kind of halfway in between. They don't do both all in one. Because for us, deployment and development are kind of mixed. You can deploy an application to somebody and they can change the code and they can reuse it. Or they can adjust some facet of it in a way that would never be imaginable in other systems. You deploy a document to somebody and that's the document. They're the people who have the document. They're the people who have the system that's there, and you are the developer and they are the person to whom it's deployed. So we have these sort of, what I call, it's a bit like wave-particle duality, right? It's like it's neither a wave, nor is it a particle, or you can say that there's a mathematical description that represents both, and there's just some way you have to overlay on top of this to think about what it is as a human. It's a bit like that with all of these. And, symbolics, numerics, they're not distinct for us. They're kind of meshed together. We have symbolic representation of numerics. We have arbitrary precision numerics. These things are not distinct. They're not discrete. Computation and coding. Traditionally, you have computation systems and you have languages. And they're kind of separate. They're not for us. They're all together. The cloud and local, I've just talked about how that's hybridized in our model of it. And data and expressions. So the way you have to think about what we have is we have this huge kind of space, this continuous space in all of these dimensions. And the question is how to piece that together optimally with the core basis that we have. So let's also talk about sort of facets of ubiquity. How do we drive computation to everywhere it can go? Well, we need to automate the insides, and we've done that rather effectively in many cases, although not all. You need to get it running everywhere so everyone can use it on any device. I think the cloud helps a great deal with that. And you need to have coverage across all the areas that you want to cover. You know, do we cover what we need in machine learning? Do we cover what we need in statistics? Do we cover what we need in interface building? All of these sorts of areas are important in terms of coverage in order to achieve that. And also, how is it productized? Do people understand what they can get when they do stuff with us? So the big question I've been working on is, how do we marry ubiquity and unification? It's a big ask. And I think, I won't go into too much detail here, but one of the things you'll be seeing emerging is we're trying to build a superstructure of what I call workflows, workspaces, platforms, and components. So the idea is that you, either as a sort of end user of something we've built, or indeed for making something for yourself or your clients or your organization, will be able to construct any take on any of these elements, any of these dualities, in the easiest possible way. And I think the way to think about that is to think first about what workflow you really want to achieve. What do you want to start with? What do you want to end up with? And how do you get between those two using the whole sum of the technology? Now, one element of that, in a sense, is how you present it and what the workspace is. And so, in a sense, being able to construct nice-looking workspaces is an important element of that. We've already started releasing some platforms, and starting on like finance platform, for example, and data science platform is coming. And the point of those platforms, in a sense, is to collect together workflows into manageable chunks that people can understand if that's all they want at that stage, in a sense. And then the components are, in a sense, the underlying pieces of chunks of technology that really service that. So, in a sense, those are the elements that we are piecing together into a sort of superstructure, and I think it'll be very exciting as this emerges. So one of the things we're making sure as a company, and we haven't always done these things particularly well, there's this expression in English, eat your own dog food. It's not as bad as it sounds. It's a software expression which means if you build stuff, you should use it yourself. And we've done this very successfully for our own computation. One thing we're driving at internally to do much harder is to use all of our development technology to develop everything we need to develop as much as possible, whether it's our own ERP system or whether it's our searches in email systems or whatever. We use our own technology as much as possible because most of these rely on computation, and as much as possible we think we should use our own technology because then we iron out all of that workflow issues that we were talking about. So we are getting better at so-called eating our own dog food. Productizing our ecosystem is, as I talked about. The other thing is we want to demonstrate the unexpected. One of the problems with our technology, these dualities I talked about, is it's hard for people who are not the sorts of people you are many times coming and visiting us and so on. It's hard to explain to them what is it that we can so cleanly do for you. And so one of the things, and I'd love to have examples from you all as you think of them, is what I call sort of pivotal examples. Unexpected examples where people would think, my goodness, I didn't know that computation could do that, or I didn't know the Wolfram ecosystem could produce that. It just seems like things that are wired together that you wouldn't expect, that seem surprising. And something I haven't talked about much here, but is absolutely central, is being the ultimate development platform. You know, many of you develop things for other people, or for your own organizations, or for yourself. And it's crucial that those things can be fitted together well, and that you can produce any of those things that you want as quickly as possible. And another thing that we're pushing on hard is to be the center of what I call computation-led data science. Data science, as I mentioned, has a long way to go. And I think we are emerging as, in a sense, the people who do innovative stuff in data science with computation. And that's a very powerful field, whether in health or finance or many, many other areas. So to summarize, we are, in a sense, computation meets knowledge. And I guess our strategy is to build the ultimate computation ecosystem with you and involving you. And I look forward to hearing all of the things in the next couple of days that we can talk about around that. Thank you very much.